very, very nice. And also thank you for staying up all the way until the end of the conference. As you have heard, my name is Antonio, and I'm at the moment a Marie Curie Fellow at University of Zagreb. But most of this work was done when I was a postdoc at University of Cambridge. So that's hence the two logos. I will talk about two projects which have in common that both of them deal with some sort of out of equilibrium localization properties, and both of them deal with 2D quasi-periodic models. So the first part of the talk was done in collaboration with Claudio from Cambridge and Elmer, who was back then in Karlsruhe, while the second part was done with Noor, who is at the moment in Cambridge, and James, who is a PhD student in Max Planck in Dresden. As I've said, the talk has two parts. The first one deals with many-body setting, so a many-body quasi-periodic model, where we looked at its localization properties. We saw, in a sense, that this localized, or maybe we can call it even many-body localized phase, is more stable than in random models, but it also hosts some other phases that are not possible to be realized in random models, and that's this weird coexistence of localization and subdimensional transport. If the time permits, I will also tell you a few words about the other project, which deals with single particle setting, but with a driven potential. There, since the potential is driven in a very particular way, namely it's rotated, we have a spatially dependent driving, and this then induces very cool features like oscillatory behavior of hopping amplitudes and some bulk localized transport states. Okay, so this is the main actor in the story. It's the system of first the tight binding square lattice depicted down there, where the lattice sides sit at the nodes of this mesh. And there are some particles hopping around the lattice with a constant hopping j over 2. On top of that, we introduced the on-site potential, which is made of two perpendicular cosine beams. And then you can play either with the angle of this potential with respect to the lattice or with its wavelength. And like that, you can make it quasi-periodic or periodic or whatever you want. To show you that this is not only a theoretical proposal, there are nowadays a couple of experiments, like very nice ones being done in a group of Uli Schneider at University of Cambridge, where they use 4 laser beams, and with that they can realize this particular model. So 4 laser beams are set up in a way that they close 45 degrees angles between themselves. And then by taking, for example, these two to be very deep, they can act as tight binding lattice, and the other two then simulate the potential. Okay, so let me now go to the first part of this talk. And just before showing you our motivation of this, let me just present the most important things I will use from this many-body localization community. Namely, I will differ between two types of systems. On the left-hand side, there are thermal systems. So we know that they're ergodic. We can use our nice statistical physics methods to obtain all sort of properties of such systems. And what is important is that expectation values of any local observable will be given by their thermal values. So even if the system is closed, if you probe it locally, it will be in equilibrium. And for our talk, for this talk, it's important that any local information, when I say information, I mean the initial state, is lost after a certain time in these systems. If you take a look at this figure, so I start in an initial null state, and if the system is thermal or ergodic, this null state will be smeared out and will become homogeneous. On the other hand, you can break this ergodicity by, for example, going to the many-body localized regime. This can be done either by introducing disorder or interactions, or nowadays you can do also like some linear potentials and so on. We will be concentrating around disorder plus interaction scheme. And these systems then break the ergodicity, and any initial state is preserved indefinitely, as you can see it here. Among many theoretical works. There were also a few very nice experiments done early on, like in 2015, 16, and so on. The first one, I just picked two, which I find very interesting. The first one was done in group of Immanuel Bloch, where they created a one-dimensional quasi-periodic chain, or actually, sorry, lattice, which mimicked the Aubry-André model. And what they see is when they crank up the potential strength, then the imbalance between even and odd sides. So first, I forgot to say, they populate the lattice they put a particle on every second side, and then the imbalance between even and odd sides at some point gets to be saturated. So the conclusion is at high enough potential, the imbalance doesn't decay anymore. And roughly a year later, another experiment was shown where they looked at a two-dimensional problem, but now they use a two-dimensional random optical lattice. And what they saw is a similar thing. So they would start, for example, look at this second and the fourth column. They would start with an imbalanced state. So they would use a domain wall and let it evolve over time. The second column shows you what's happening if you don't have any potential turned on. And you can see that eventually the cloud homogenized a bit. While if you crank up disorder, then the cloud stays what it seems to be still a domain wall for a very long time. And this you can, again, probe by the imbalance. So at the beginning, this wasn't any, like, I would say, it wasn't such a big surprise because you have Anderson localization in 1D, you can have it in 2D, so you have many-body localization in 1D, why won't you have it in 2 dimensions? Well, roughly at the same time, a very nice theoretical argument of instability of such a phase appeared, and it was coined mostly by Dirac, Hueniers, and Imbri, where they said that actually we should not expect MBL in any dimension larger than 2. And the reason is the following. So I'll just sketch the argument and will not go so deep into it. But just imagine that you have a very large random system. Then in this random system, there is a probability, although being very small, there is a finite probability that you will find a spot, like a bubble of sides which feel very low disorder. And this is what I depicted here with the red color. Now this bubble will be thermal because it doesn't feel essentially any disorder, and it will want to hybridize this blue background, which is heavily localized at the moment. Now, to hybridize the outside two-level systems, this two-level system has to see the bubble as a continuous energy spectrum, so like a good path, right? Because then a spin flipped can be accommodated by some process inside the bubble, so energy is conserved. This bubble is connected to the outside spins only weakly, so with the coupling that decays exponentially, and then it wants to grow, right? It will grow all the way until the outside spin, or like a two-level system, sees the thermal band as a set of discrete energy levels because the spin flip cannot happen then anymore. So it will grow until a certain length. Well, this is true only for one-dimensional systems, and the reason is the following. So you can create this condition of hybridization, which is just the ratio between coupling matrix element, which decays exponentially here, versus the level spacing. Now, this is proportional to the, as I said, coupling to the outside spins and also to the square root of density of states. And the whole trick is that even though the coupling is decaying exponentially, this density of states increases when the bubble gets larger and larger. In one dimension, it also increases exponentially. So there is a competition, which at some point will bring you this ratio to 1, and then thermalization will stop. But if you go to 2 and higher dimensions, then this growth of density of states is super exponential, and therefore it will never stop. There is an avalanche occurring, and the system is being destroyed, even if you have a single thermal bubble in it. For that reason, we decided to move away from random systems and take a look at another class of systems that show Anderson localization, and those are the quasi-periodic ones. So we looked at in particular at the Aubry-André model, which is again a lattice now populated with many particles at half filling actually, and it has an on-site potential which has actually two variables in it. One of them is the angle that it closes with the lattice, depicted here on the left. This is phi. And the other variable is its wavelength compared to the lattice, which we take to be incommensurate. Therefore, the model is always quasi-periodic. So the Hamiltonian has a simple hopping term nearest neighbor interactions, which are constant, and the potential, which I said it's made of two cosines, and this u and v are connected to the lattice x and y with the simple rotation with an angle phi. So now, out of many possible generalizations of this O'Brien-Drake model with respect to the rotating angle, we chose only two. One of them is when the potential is aligned with the lattice. That's when phi is 0. This one is known as the separable model. And the other model is when the lattice is rotated as an experiment with 45 degrees compared to the lattice. This one is known as the non-separable model. The reason why we chose those two is because they're least probable to host any stable localized phases. And the reason are so-called weak potential lines. So for example, take a look at this non-separable model. I can write my potential instead of sum of two cosines. I use the trigonometric identity to write it as a multiplication of two cosines. Now for any y, you will have an x-dependent potential strength. And since this cosine is quasi-periodic, this x-dependent term can be arbitrarily small. So every now and then, in the lattice, you will find that there is a line, like over all y's, which has arbitrarily weak potential. The same happens in x direction. And here I only showed two of them, but in fact, there's a whole mesh, which is quasi-periodic. It has dimensions smaller than 2, but it's present in any size of this potential. In a separable model, similar thing happens, but now these weak potential lines or WPLs are rotated by 45 and they lie on diagonals. So they don't connect nearest neighbors, but next nearest neighboring sites. This has a big impact on the single particle physics, which was known from before. So in the separable model, you can find a localization phase transition at a self-duality point. So at this point, all the states in the spectrum localize simultaneously and remain localized for any larger disorder strength, potential strength. On the other hand, in the non-separable model, you will find some delocalized states which live on this mesh of weak potential lines for any value of W over J. So essentially for any potential strength, except for, of course, infinity. Now, this was all known prior to our work, and then we thought, okay, what happens if we put now many particles, make them interact, and if these two models seem to be stable upon localization, then any other rotational angle should also host a stable MBL phase, or like localized phase. So to study the localization in a many-body setting, we opt to do the same as in experiments, namely we investigate the particle imbalance. It's written here for a specific initial state, but we actually use different formulas for different initial states. And it's exactly the thing they used in experiments. Since the problem is very difficult to attack analytically, we do most of our calculations using numerical method of time-dependent variational principle. It's a cool MPS-based method which can treat systems where entropy doesn't grow too fast, so localized systems. And as I said, we will try different initial states, for example, checkerboard, columnar density wave, or a random initial state to see whether some of the characteristics are stable or not. Okay, so that being said, I show you the first result. And that's the result for a system which has roughly 80 sites. And I plot the average imbalance, so I average over different potential realizations as a function of time. And I plot it for the non-separable model and the separable one. As you can see in this log-log plot, imbalances decay linearly, which means that they have an inverse power law decay. And a nice thing about that is that this gamma then can serve as a measure of localization. So when gamma is 0, then the imbalance is saturated, the system is localized. When it's finite, the system is still weakly ergodic. And you can see in these two insets that gamma indeed decays, and roughly at W over J is equal to 20 in both models, it hits 0. So there is a localized phase when W is larger than 20 times J. Next thing we did is we tried to scale the system size to see if this transition point is stable when we scale the system. And we saw that it is. So for different system sizes, you can see that the curves of gamma versus W lie on top of each other, which means that this is a good hint that this could be in principle that the phase could be stable even in the thermodynamic limit. Although this is very tricky to claim on a system with 100 signs, right? But it's very much different from the random case. So I did the same with a completely random system. And you can see that now the transition point drifts towards higher values if you increase the system size. And that's actually because of these avalanche mechanism that I showed you at the beginning, and shows why the two-dimensional random systems cannot be stable in thermodynamic limit. So the conclusion is that quasi-periodic ones seem to be better candidates to host stable localized phase compared to the random ones. So now, what about these weak potential lines that I showed you that had a crucial effect in the single particle regime? Well, since I average over many systems and the systems are order of 100 signs large, I will not hit the weak potential line in every sample, right? So what I did is I specifically concentrated on the samples that had them. So I created two sets of samples. The left one has the weak potential line in the middle, shown here. And the right set of samples don't have it. The average is done in such a way that the potential is moved left or right, such that this weak potential line stays always in the middle. And you can see that there's like the time evolution shows some dynamics only at the point where the weak potential line exists. This can be observed also in the averaged imbalance of the system. So without WPL, the imbalance saturates more or less immediately, while with it decays slowly. Now, if we want to check if the transport is indeed happening at the weak potential line, we can calculate the averaged row dependent imbalance, which actually gives you a one-dimensional particle imbalance, but for each row in our sample. And you can see that most of them are saturated, except the one which coincides with the spot where the WPL is. On the other hand, without WPL, everything is saturated immediately. And if you apply different initial states, the story holds exactly the same. So the conclusion is the rest of the system remains localized while some transport is being present on the weak potential line. Okay, so this was an easy system. Let's go to the separable model, which I remind you has the weak potential lines along the diagonals. So particle has to hop from one side, which doesn't have any disorder, to the disordered side and then back. And then it's not clear what will happen. But if you just run the numerics, you see that if the samples have WPL, the imbalance decays, indicated some transport, and without it, it stays constant. And now instead of looking at the one-dimensional row-dependent imbalance, I look at the one-dimensional diagonal-dependent imbalance. So J0 means the main diagonal, and plus and minus 1 and 2 are the two neighboring diagonals to the main one. And then you see that, again, that there is transport occurring at the main diagonal where the WPL is, and everything else remains perfectly flat. Now, if you go in the ergodic side of the phase transition, then everything decays as you would expect. This is a bit weird because I show you that all single particle states are well localized for such choice of W, and there is still some transport. So there is something special about many body state which makes the transport happening. And it's even more interesting if you plot different initial state, namely, for example, random one. You see that this transport gets to be very suppressed, like it's barely occurring. We wanted to see why is this happening. And to see that, we wanted to, first of all, simulate larger systems. And secondly, we wanted to do some analytics on top of it. And to do so, we cut out the three diagonals of our system, the main one and the two neighboring ones, and made it into a quasi one-dimensional diamond chain. Now, this will allow us to simulate much, much larger systems, and you can even do some analytics for single particle properties. So now there are three sides per unit cell. The middle ones are representing the weak potential line, so they are at zero potential, and the upper and lower ones are feeling some quasi-periodic potential, which is mapped from the 2D ancestor model. Now, to fully represent our previous system, where we initialize the system in a columnar density wave, we fill out some sides according to the 2D model. And we suppose that, we assume that actually the sides which are not lying on the WPL are heavily localized. So these sides which are not colored with blue don't do anything. They're localized, their particles are sitting on them and stay there forever, which means that the particle which is sitting here in the middle to move to the next side has to do this zigzag movement. So it's effectively moving along a one-dimensional line. This one-dimensional line can be described by, again, simple 1D model, and the model is called the mosaic model. And the main characteristic is that it has two sides, A and B, where A has a constant potential, and B's are actually quasi-periodically disordered. You can solve it completely analytically. An interesting thing is that in single particle limit, it has a mobility edge. So there are states which are delocalized for any choice of a potential strength. And this is crucial because now if you sit at some very large potential strength, you hybridize all those single particle states by introducing many particles and interactions. And what you will see is that this delocalized states actually destabilized the many-body localized phase and allowed for some transport. And this is what we observe. So there is an imbalance which decays for every choice of W over T, and we go all the way from 1 to 30 or even 50 or 100, and we always see some transport. So to recap, because of the choice of the columnar density wave, we blocked some sites in this diamond chain, which makes the particles feel effectively the mosaic lattice, and this mosaic lattice has extended single particle states, which then delocalized the localized phase. Okay, so this was it, everything regarding the first part. So how many minutes do I have for the second part? 2, 1, 2. Okay, then I do it very quickly. Only 3 slides. In the second part, what we did is we removed all the particles except one, so it's a single particle physics. And instead of keeping the potential constant, we rotate it with a constant velocity omega. Now, this will introduce the time dependence into the angle phi. And it's a bit weird drive compared to all the other ones from the literature because it is spatially dependent. So if you plot the Fourier coefficients of your potential, you see that, and you plot it as a function of the radial distance from the axis of rotation, you can see that the maximal frequency contributing to each side actually depends linearly on R. Moreover, the amplitudes of the Fourier coefficients decay with this distance from the axis of rotation. This is easy to imagine. Like if you are very close to the axis, you see only few maxima and minima when the potential is rotated. And if you're far away, you see many of them, so you need many frequencies to describe it. Then we do the standard gauge transformation, move the time dependence from on-site to the hopping. As I said, because if you are very far away from the axis of rotation, then your driving will have a limited effect because it essentially averages to 0. And what we saw actually is that the system experiences some sort of average dynamical localization because the quasi-energy spectra gets to be shrinked. And this can be qualitatively captured by the Bessel function behavior of the neighboring hoppings. But this is the last slide. What is more important is that these effective hoppings now have some spatial dependence. Namely, they will form these nice circles, so they oscillate in radial direction, and they oscillate from being very small to being very large. Now, these regions, ring regions with a large hopping, will then induce states in this quasi-energy, which are also ring-shaped, and they can then support the annular transport, right? I initialize my initial state here, and after waiting some time, it will cover the whole circle, and it will not explore the rest of the system. Okay, with this, I'd like to thank you for your attention, and yeah, sure we will complete it. So a plot in the argument is a good plot. Here, as you can see, like on this second plot, the network of the network is essentially locally quasi-operation. It's involved. Because they're not. Well, the question is, what will happen if you fail in the system? And then it's important to have but if you focus, happens the stronger the disorder, the more you decouple the line, the less. And just like there's no compensation, and there is no opposite effect. The native doesn't know. But this is all about the say it's part of the so all we offer is a single and it's not so we raised that some of us makes